Right, so let us now start the exercises based on prime factorization. The first one is of course extremely basic, and you just have to look for the factor, search for the factors, and you will see, the prime factors of these numbers, and we will see that they are just these. Three, 5, 2, 8 turns out to be equal to 2 cube times 3 square times 7 square. Then the second number 30,030 is actually the product of the first 6 prime numbers. That means 2, 3, 5, 7, 11 and 30. And this last number $220,000 equals 2 to the power 4 times 5 cube times 11. So these are just the prime factors. Actually we were not asked to just find the prime factors, but in fact we were asked to factor the numbers. So these are the factorizations. Then show that for every prime p greater than 3, there exists a positive integer k such that p is 6k plus 1 or p is 6k minus 1. By the division algorithm, we know that there exist integers okay, let us take q because we can figure out k later. Q and r such that p will be equal to 6q plus r, where R takes these values. That means we are dividing P by 6. So Q is the quotient and R is the remainder. Okay. Now note that should we write like this, note that, or yes, there is in fact no need to ascertain non-negativity of Q. That's what I was thinking. That we can do. But first let us observe that R takes 6 values. Okay. Originally R takes 6 values because R satisfies these inequalities. So R can either be 0 or 1 or 2 or 3 or 4 or 5. Some of them will be ruled out. We will see. Then R is 0 or 1 or 2 or 3 or 4 or 5. These are all the possibilities. Correspondingly, P is 6Q or 6Q plus 1 or 6Q plus 2 or 6Q plus 3 or 6Q plus 4 or 6Q plus 5. Let us first argue that P cannot be equal to 6Q. Since P is positive, if P is equal to 6Q, then Q must be positive too, naturally. But then six divides P, which is not possible. Why is that not possible? That is because P is given to be a prime number. So if 6 divides P, then 2 distinct primes divide P, 2 and 3, and that is not possible. So P cannot be equal to 6Q. So this possibility is ruled out. To show that this is ruled out, let us put the this equation within inside a square. Okay, next what we try to rule out is this: if P is equal to 6Q plus 2, then 2 divides P. divisibility relation all by itself does not contradict anything, but additionally we are also given that p is greater than 3. So the only possibility where this was true was the case where p is equal to 2. That however now is not possible because p is given to be greater than 3. Since p is greater than 3, this is not possible. That means this is also ruled out. Next, if p is equal to 6q plus 3, then 3 divides p, and that is also not possible because p is greater than 3. Three divides p, this is not possible because p is greater than 3. So that means this is also gone. Next, this one 6q plus 4, we will see that that is also not possible. If p is equal to 6q plus 4, then 2 divides p, and we have already seen that this is impossible. So that means this condition is also gone. So we are left with only two possibilities, 6q plus 1 and 6q plus 5. Thus, p is equal to 6q plus 1 or p is equal to 6q plus 5. Okay. Now note that we have been asked to show that p is of the form 6k plus 1 or 6k minus 1 where k is a positive integer. If p is equal to 6k plus 1, then definitely q is positive. Do you see why? Q cannot be equal to 0 because then p would be equal to 1. 1 is not a prime number, and q cannot be negative because then this would be negative. Okay, so that's why q must be greater than 0. So that means in this case p is of the form 6k plus 1 where k is equal to q, which is positive, which is a positive integer. If on the other hand p is 6q plus 5, then p can also be written like this, plus 6 minus 1, and that is this minus 1. Okay, now what about this q plus 1? We want this q plus 1 to be our k, that means we want this to be a positive integer. For that to happen, q must be a non-negative integer. Now, is it possible here for q to be a negative integer? In the largest possible case, where q is equal to minus 1, this becomes minus 6 plus 5 minus 1. And if you have higher negative values means more negative values of q, then you get more negative p, but p is not negative, so that's why q must be greater than or equal to 0. Since q plus 1 is a positive integer, that's what we wanted to show. So this completes the solution. Next, 23. Let p be a prime and n an integer. Show that either p divides n or the greatest common divisor of p and n is equal to 1. Okay, let me just refill first. Okay, so now we are given any integer n and a prime number p. We have to prove that either the prime divides n or they are relatively prime. If p divides n, then there is nothing to prove. So assume that p does not divide n. since the only two positive divisors of P are 1 and P. That comes directly from the definition of a prime number. The only two positive divisors of a prime P are 1 and P itself, and one of them does not divide N. So this P, although it divides P, and but because it does not divide N, it fails to be a common divisor of N and P. And because of this, the only positive common divisor of N and P is 1, because 1 is a divisor of every integer. So 1 is always there in the list of divisors of a given integer. 1 is an element. So 1 is a common divisor of N and P, and that is the only positive common divisor. So that is also naturally the greatest common divisor, greatest positive common divisor. Hence, one is also the greatest common divisor of N and P, that is this is equal to 1. So that completes this third solution. Then use induction to prove corollary 2.4. So that means it's that corollary which says that if a prime number divides a product of any number of integers, then it divides at least one of them, which is a corollary to the result that if a prime number divides a product of two integers, then it divides at least one of them. This is that corollary to this result. However, I forgot to write the number of this result. So we will somehow mention it, because we will need this result in the corollary. Let us first recall the statement of the corollary. This, however, you need not do when you write the actual solution. You can just start the proof in the solution itself. However, for our convenience, we will now recall the statement of this corollary. Let P be a prime number. And these are integers. If P divides the product of these integers, then P divides AI for some I. For some I means for some I here from 1 through n. Among these suffixes, some suffix I for which AI is divisible by P exists. Oh, okay. This is the solution itself now. So let us write proof. We apply induction on n. Because nothing has been said about n can in fact be 1, in which case the statement is trivial, because in that case we have only one integer a1 and the hypothesis is that P divides a1 and the conclusion is that P divides ai for some I, because the only available I in this case is 1, so P divides a1, which is true. Okay. The result is trivially true when n is equal to 1. When n is equal to 2, we know that the result is true. How do we know? Actually, this is coming from that result, which is a lemma or theorem, I don't remember, to which this is a corollary. Okay, that two case where P divides AB, then P has to divide either A or B or both. So that's why, because we don't know means I don't know, I have forgot to write it here, so we will have to write something like this, a little vague. You write the actual result. Okay, we know that the result is true because of that theorem or that corollary. Assume that the result is true for some integer n greater than or equal to 2, because we have seen the case 2, so now we will use an inequality like this. We will look at a higher stage. Let an plus 1, let these be all integers such that P divides their product. Then P divides this, or P divides an plus 1. From this relation, we get this conclusion by using the case n equal to 2, because this product of n plus 1 integers can also be regarded as a product of two integers, one of which is this product and the other is an plus 1. So that's why, because P divides their product, so P either divides this one or this one. By the induction hypothesis, P divides AI for some I satisfying this, because this is a product of n integers and we have assumed that the result is true for a product of n integers. So P has to divide at least one AI from here. So that means either P divides A1 or A2 or A3 like that, or P divides AN. Combine that with this one, or P divides AN plus 1, we get our induction step. Hence, n plus 1. This completes the induction, completes the proof, and also completes the solution. Then I hope I have written corollary 2.4, not corollary 2.24. It's corollary 2.4. Okay. Next, the exercise number is 224. Next, 25. Exercise number. Let P1, P2 and so on up to Pk be any primes show that for each I, Pi does not divide this product plus 1. Although looking at these notations, it seems like the primes are distinct. That is not necessary. All of these may be the same prime. However, that is not something we should be concerned about. We are just given some k number of primes, not necessarily distinct. We have to prove that no prime from this list divides this number. That's what we have to prove. This proof is by contradiction. Suppose, and for each I here in this context clearly means for each I varying from 1 through k. Suppose there exists an I for which actually Pi divides that. A few words about this type of writing. When you see a sentence like this, suppose there exists some this for which something is happening, it really means this. Suppose there exists some I satisfying these inequalities for which this is happening. Usually we don't write such a long sentence, we contract it in this way. It looks somewhat strange, but it saves a little time. Okay, this is common practice. Since we also have Pi dividing this product, and why is that so? That is because Pi is one of these primes, so it will naturally divide this product. It must be the case that Pi divides this number minus this number. That is, Pi divides 1. But this is a contradiction. Because no prime divides 1. Hence, our supposition is wrong. That is, pi does not divide this integer for all I in this range. (26) Use the preceding exercise to show that there are infinitely many primes. So this previous exercise and this one, they actually constitute the well-known Euclid's proof of the fact that there are infinitely many primes. So this is from Euclid. So suppose there are only finitely many primes. Many primes, and let those primes be these. Say these are the only available primes. We don't know how large k is, but it's a positive integer. That is our supposition. Now consider the positive integer n . Okay, so we considered this positive integer. It's clear that n is greater than 1 because this integer itself is a positive integer. Since n is greater than 1, so if we have a positive integer greater than 1, then the fundamental theorem of arithmetic tells us that it is divisible by at least one prime. Any such integer has some prime factor. There exists by the fundamental theorem of arithmetic f prime p such that p divides n, since according to our supposition, the only primes are these. So that means P must be one of them. We must have P equal to Pi for some I in this range. But then Pi divides n means Pi divides this number. Which contradicts the previous exercise. So our supposition is wrong. That means there are infinitely many primes. Fundamental theorem of arithmetic, the fact that it allows us to break up the integer into its prime constituents, is somewhat like the atom smashers, the particle accelerators, like the one you have in Europe, which allows us to break a physical object, a material, into its constituent parts. So it is somewhat like that. Supposition is wrong. That is, there must be infinitely many primes. This proof is really remarkable. I mean, the proof is quite simple conceptually, but using that kind of simplicity to achieve a result like this is really the mark of a genius. Then let P be a prime and let A and N be positive integers. Suppose that P divides A to the power N. Show that p to the power n also divides a to the power n. The problem with these inconsistent notations is that I forgot, right now I don't remember what n stands for here in this book. Specifically whether n has or does not have the integer 0, that I forgot in Gregory Tilly's abstract algebra. So I don't really know whether a and n are allowed to be 0. But even, okay, no, that cannot happen. Because, for example, if okay, is it possible to have a or n or both of them equal to 0? If a is non-zero and n is 0, then of course this divisibility relation itself is false. Anyway, the point here is that that does not really matter, and that does not affect this thing, because it's already given that p divides a to the power n. So without thinking of such minor things, we can start from here. Since p divides a to the power n, corollary 2.4 implies p divides a. Why? Because p divides a product of n number of a's. So that corollary says that if p divides such a product, then p has to divide at least one factor. In this case, all the factors are a, so p must divide a. But then a is equal to pk for some integers, for some integer k. This implies a to the power n is equal to p to the power n times k to the power n. But that in turn implies that p to the power n also divides a to the power n, and that's just it. Next, exercise 28. Let p1, p2 and so on, pk be distinct primes. Okay, this time distinctness is given. And let mi comma ni, where I of course is changing likely from 1 through k. Let this be non-negative integers. Find the GCD of these two integers. And p1 to the power n1, p2 to the power n2, up to pk to the power nk. Consider the integer d equal to p1 to the power minimum of m1 and m. Okay, I think it's better to write it using some more notation. M, N, O, P, Q, R, S. Okay, let us take S. Where Si is the minimum of Mi and Ni for I varying from 1 through k. Note first of all that this d makes sense and is a positive integer, because mi and ni are whatever I is, these are non-negative integers. So their minimum is either mi or ni, which is a non-negative integer. So each si is either mi or ni. So that means this is a positive integer. Note that t is a positive integer, since Si being the minimum of Mi and Ni is less than or equal to both Mi and Ni. So we must have d dividing. Okay, now we could have named these integers something, but it's okay. D divides this, and t divides this. Okay, why? You see, say you take I equal to 1 and suppose the minimum is m1, then here the first factor, the first power of p1 is p1 to the power m1. Now p1 to the power m1 is here available in this number, and that p1 to the power m1 is also available here because m1 is less than or equal to n1. Like that, considering the other i's, you will see that every time we are taking, when we are forming this number d out of all the prime powers of the pi's, we are taking the least one, the least prime power. So naturally d would divide both of them. That's why. Now let let E be a positive integer such that E divides the first number and also E divides the second number. If E itself is equal to 1, E has been chosen to be a positive integer, so either it is equal to 1 or it is greater than 1. If E is equal to 1, then obviously E divides D. Okay, so assume E to be greater than 1. Now because E is greater than 1 by the fundamental theorem of arithmetic, E itself will have a prime factorization. Theorem of arithmetic Okay, so E will have a prime factorization. What are the primes that can appear in that factorization? Those primes cannot be anything other than these primes, because if you have something else here that is none of these primes, then that prime, being a factor in the factorization of D, divides D, so that prime should also divide this. However, in that case, that prime should divide at least one of these factors. Okay, and that would imply that that prime divides at least one pi. But because that pi itself is a prime, so this prime and pi must be equal, which is not true, because the prime that you have in the factorization of d we have chosen is outside of this list of primes, all these pi's. So that would give us a contradiction. So that means the primes that appear in the factorization of d must be from among these. So we write directly, okay. So we have used only these primes in the prime factorization of E. Where to account for the fact that maybe all the pi's are actually not present in the factorization of E, we will allow these ti's to be non-negative, so that some of them can be 0 and those corresponding primes will actually not appear in this factorization, okay, where the ti's are non-negative integers. In writing this or in concluding this form of E, we have not only used the fundamental theorem of arithmetic, although we have written only that, it seems, but we are also using this fact, not this fact, actually this relation and this relation, or in fact any one of them. So now we have the factorization of E in this form, but the ti's are non-negative integers. More is true, since E divides these numbers. We additionally have ti less than or equal to mi and ti less than or equal to ni for all I here. Because if, for example, t1 becomes greater than m1, say, then E will fail to divide this, because then the power p1 to the power t1 would be more than the power p1 to the power m1. So then how can E divide this? Because E is dividing this means what? p1 to the power t1, that power alone is also dividing this, because that divides E. But then if t1 is greater than m1, that will fail to divide this. The other part, the rest of the things in this number, actually don't play any role in this division of this number, this integer, by p1 to the power t1. Only this part, this power of p1 plays a role. So in order to have full division, t1 must be less than or equal to m1. It can be at most m1 but not more than that. That's why we have this, and similarly that one for all the i's. Thus ti is less than or equal to actually si, which is the minimum of mi and ni. This in turn implies that E divides D. Okay, because now in D the factorization of D looks just like this, but the exponents are the SI's, and those SI's are all greater than or equal to Ti. So naturally E would divide D, since E and D are both positive integers. We thus have E less than or equal to D, and that comes from this divisibility relation. So what is it that we have shown here in this solution? We have shown that D divides both the given integers. So D is a common divisor, D is positive, and D is the greatest among all positive common divisors. So it is the greatest common divisor by definition. Hence D is the greatest common divisor of the given numbers. Now you may be wondering, after seeing this solution and after seeing the form of the greatest common divisor, that if finding the GCD is this easy for these two integers, then why do we need the Euclidean algorithm? That's because finding the GCD in this way is easy only if you have the factorizations of the original integers into their prime factors like this. If you are given any arbitrary integer n, it's in fact very difficult to find its prime factorization. It in fact becomes sometimes very difficult to find even one prime factor for a given integer n. That is because sometimes the prime factors of n themselves are extremely large. And this fact is used in RSA crypto system to generate secured systems of enciphering some message that cannot be easily broken by taking two extremely large primes, multiplying them, and then doing something. We will see at one point when we go to those parts of number theory. So unless you are given these factorizations, you cannot really use this formula. this formula or this form of the GCD is useful in some theoretical situations. You can readily say some things about the GCD from its form alone. In general, we have our that familiar thing which can be, although it may be time consuming, but it is much easier to apply, the Euclidean algorithm. Okay, so with this solution ends and this set of exercises also ends and the video also ends. So we will see further things on these things next Saturday, and tomorrow we have our analysis video. So that will be all for tonight. If you want to say something about these things, you can use the comment section or you can mail me at my usual address. So see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.